Hello everyone, this is Sachin Tripathi, a fifth year PhD student from University of Connecticut and currently working under Dr. Malla. Today I'm going to talk about a part of my research which has a title of Finite Element Modeling of century-old Tilton-Belmont Railroad Bridge in New Hampshire under typical train load. To introduction, most railroad bridges in the United States are built in the late 19th and early 20th century. So it has been a while since they have been constructed. So it is of utmost importance that we have to extend the life of these critical transportation assets. And for that, we have to have effective and efficient structural health monitoring techniques. In this slide, um, on the left hand side of figure 1, we have a Tilton-Belmont New Hampshire bridge. And the right hand side is basically a edge-built drawing that we obtained from New Hampshire Department of Transportation. Now going into objectives, with a large number of bridges in the United States approaching the end life of their design service life, the primary goal of this research is to develop a strong and economically viable system for evaluating structural health through the use of cost-effective approaches. So for that, we have used Tilton-Belmont Railroad Bridge situated in New Hampshire State as a representative bridge. This bridge was constructed in 1893 and it is basically a single span railroad steel bridge with an open deck truss, and it consists of single railroad track. This bridge is being traversed by passenger and freight trains occasionally. So going into specific presentation objectives, the first one is to develop the finite element model of the Tilton-Belmont New Hampshire bridge using the edge-built building drawing which has been provided by New Hampshire DOT. The second objective is to conduct the modal analysis of the bridge and determine their dynamic characteristics such as natural frequencies, mode shapes. And the final objective is to determine the displacement of the bridge, basically static in this case under the freight train. Going into the methodology, from the edge-built drawing that has been provided from the New Hampshire DOT, we developed a three-dimensional model of the bridge, and basically it was created using 483 members in wire elements with 33 different cross sections corresponding to eye bars, stringers, floor beams, and diagonals. And in order to develop this model, we use the commercial finite element software Abacus, and figure 2 in this slide provides the rendered view of three-dimensional finite element model, wire model basically of the bridge. In total, we have 736 elements, out of which 645 are corresponding to beam element and 92 is corresponding to truss element. Regarding the beam element, we use top chord, rails, ties, stringers, and floor beam. And bottom chord, diagonals, sway bracing, and lateral bracing were used as a truss elements. Regarding the boundary conditions, we consider simply supported. So basically hinge on the left hand side and roller on the right hand side. Once the basic finite element model was developed, we conducted modal analysis, and subsequently we conducted static analysis to determine the vertical displacements at different points on the bridge. For that, basically what we have used is the standard 4XL car configuration that is used for bridge rating, and the configuration of the train has been provided by New Hampshire Department of Transportation. And for that, we conducted static analysis for 4 different conditions. So basically the first condition is when the freight train with cars of 263,000 pounds covers 1/4 part. The second case is half of the bridge is fully covered by the freight train, and case C is basically 3/4 of a bridge is covered by the train, and the final one is the bridge is fully covered by the freight train. And discussions. The first thing we did was model analysis of the developed finite element model corresponding to Tilton-Belmont bridge, and we determined the different natural frequencies and mode shapes of this bridge. And so basically left hand side of this slide provides the different mode shapes such as figure number 4 and 5. So basically, as you can see in figure number 4, the first mode shape was lateral mode that occurs at 1 Hz, followed by, and also the second lateral mode shape was observed in 1.9 Hz. Similarly, in figure 5, the first vertical mode shape was observed in 1.2 Hz, which is located in left hand side, and the similarly, first twisting mode shape was observed in 2 Hz. All these results, along with other additional results based upon the ascending order of natural frequency, has been provided in the table. So basically, first 8, and as you can see, the first lateral occurs at 1, followed by first vertical at 1.2, second lateral at 1.9, first twisting at 2, third lateral at 2.4, fourth lateral at 2.6, and second vertical at 3 Hz. So once the model analysis was conducted, we conducted the static analysis under different train loading condition. So this slide provides the deflection of a midpoint of the bridge versus the different train loading condition. So basically, when the train covers 1/4 part of the bridge, half of the bridge, 3/4 of the bridge, and when the train wholly covers the bridge. And these results are provided by blue color curve, red color curve, yellow color curve, and finally by the eggplant color curve is shown in the figure. As we anticipate, the maximum static deflection on the midpoint occurs when the train covers the bridge fully, and it is observed, it is shown or demonstrated by the eggplant color curve. And the maximum deflection of 4.32 millimeter was observed in the midpoint of the bridge. After this static analysis, what we are basically doing is we are currently working on developing the Fortran based deload subrouting, and this deload subrouting is basically a subrouting written in Fortran, and basically we can make our train load automatic. So basically we do not need to consider different cases, and we can start the load, and then like it will traverse the bridge, and then we can get the deflection with one program rather than doing multiple static analysis, and that's what we are currently working on. So going into the conclusions, basically the preliminary finite element model has been developed and is under the process of refinement currently. The dynamic characteristics of the bridge has been determined, including modal analysis and vertical displacement at different locations on the bridge under freight train, which I just presented a couple of slides before this specific slide. So basically, we would like to acknowledge the financial help of USDOT Region 1 UTC under grant 698-355-1847-101 from the US Department of Transportation's University Transportation Centers Program, and in the University of Connecticut for supporting the project financially. We would also like to extend our deepest gratitude to the other supporting organizations listed below: Metro North, DOT, Polytech for providing us instruments, New Hampshire DOT, Connecticut DOT, University of Maine TIDC, Amtrak, and GNW.